Hey everyone, and welcome back to the channel. Today, we're venturing into the coldest, most remote corners of our solar system. Forget the North Pole in winter. We're talking about temperatures that make even liquid nitrogen seem balmy. This is the realm of deep space, and it's where the future of resource gathering lies. But how do you even begin to build machines that can operate, let alone mine, in such extreme cold? This isn't just about putting on a winter coat. This is about redefining engineering itself. So, what are we talking about when we say extreme cold? On Earth, the coldest temperature ever recorded was about -89 degrees Celsius. In deep space, say on a moon of Jupiter or out in the Kuiper Belt, temperatures can plummet to below -200 degrees Celsius. At these temperatures, materials behave in completely unpredictable ways. Steel, which we think of as strong and reliable, can become as brittle as glass and shatter with the slightest impact. Rubber and plastics lose all their flexibility and crack apart. Even the lubricants that keep gears moving would freeze solid, seizing up any machine instantly. This phenomenon is called cold embrittlement. It's one of the biggest headaches for engineers designing deep space equipment. Imagine a giant mining drill on a distant asteroid. As it starts to dig, the stress and vibrations would be enough to cause its metal components to fracture catastrophically. The entire multi-billion-dollar mission could fail in a split second. To get around this, we can't just use standard off-the-shelf materials. We need to create custom alloys. Scientists are experimenting with nickel-based superalloys and special types of titanium alloys. These materials are engineered at a molecular level to maintain their ductility, their ability to bend and deform without breaking even. Cryogenic temperatures. Another fascinating area is metallic glasses. These are metals that have a disordered, amorphous structure like glass, rather than a crystalline one. This unique structure prevents the formation of cracks that would normally spread through a regular metal lattice in the cold. It's like trying to tear a piece of fabric versus shattering a pane of glass. The fabric just stretches and deforms. But it's not just about the structural integrity of the machine's body. What about the electronics? Your smartphone starts acting up if you leave it in a cold car overnight, right? Now imagine what happens at -200 degrees. The silicon in computer chips behaves differently. Electrical resistance changes, and solder joints can crack due to thermal stress. Breaking circuits. This is where the concept of heating versus insulating comes into play. You might think the obvious solution is to just heat everything. Stick a bunch of powerful heaters inside the mining rover to keep it toasty. The problem is power. In deep space, power is an incredibly scarce resource. You're far from the sun, so solar panels are much less effective. Running heaters constantly would drain your batteries in no time, leaving you with a very warm, but very dead piece of equipment. So, a more elegant solution is a combination of strategic heating and advanced insulation. Engineers use something called multi-layer insulation, or MLI. You've probably seen it on spacecraft. It's that shiny, gold or silver foil-like material. It's essentially a space blanket on steroids, consisting of many thin, reflective layers separated by a vacuum. This design is incredibly effective at preventing heat from escaping through radiation, which is the primary way things lose heat in the vacuum of space. So, you can use small, targeted heaters just for the most sensitive electronic components, the brains of the operation, and then wrap the entire module in this super insulation to trap that precious warmth. This is far more energy efficient than trying to heat the whole machine. Now let's talk about the moving parts. A deep space mining operation will have drills, robotic arms, conveyor belts, and wheels. All these things need to move smoothly. As we mentioned, traditional oils and greases would be useless. They'd turn into solid wax. So, what's the alternative? One approach is to use solid lubricants. Materials like graphite or molybdenum disulfide can function as lubricants even at cryogenic temperatures. They work by creating very slippery layers at a microscopic level, allowing metal surfaces to slide past each other without seizing. Another, even more futuristic solution is magnetic levitation. Instead of using traditional bearings that require physical contact and lubrication, you could have key components levitate on powerful magnetic fields. This means no friction, no wear and tear, and no need for lubricants that could freeze. Imagine a giant drill bit suspended in a magnetic field, spinning at thousands of RPM without ever touching the sides of its housing. It sounds like science fiction, but the technology is already used in high-speed maglev trains right here on Earth. Adapting it for the harshness of space is the next big challenge. And then there's the very act of mining itself. How do you drill into a substance that is as hard as rock, but is actually frozen gas or ice? The materials on these distant bodies aren't like the dirt and rock we're used to. You might be mining frozen methane, nitrogen ice, or water ice mixed with silicate dust. Drilling into these substances can be tricky. Use too much force or speed, and the friction could generate enough heat to instantly vaporize the material you're trying to collect. The ice would turn directly into gas, a process called sublimation, and you'd be left with an empty hole and no resources. To solve these, engineers are designing thermal drills. These drills use controlled heating elements at the tip to gently melt or sublimate the ice in front of them, while a vacuum system sucks up the resulting gas or liquid. It's a much more delicate and precise process than the brute drilling we do on Earth. It is less about breaking rock and more about carefully coaxing the resources out of their frozen state. All of these systems, the advanced materials, the targeted heating, the solid lubricants, the thermal drills, they all have to work together perfectly, autonomously, for years on end, millions of miles from the nearest mechanic. This requires incredibly sophisticated AI and robotics. The mining equipment needs to be able to diagnose its own problems. For example, if a sensor detects an unusual vibration in a wheel motor, the AI would need to determine if it's because the terrain is unexpectedly rough or if a bearing is starting to fail due to the cold. It might then decide to reduce speed, reroute power, or even switch to a backup motor, all without human intervention. The communication delay with Earth would be too long for real-time control. The research and development happening in extreme cold engineering is truly pushing the boundaries of what's possible. We're recreating materials that defy our everyday understanding of physics and building. Robots smart enough to survive in environments more hostile than anything on Earth. These technologies won't just enable us to mine asteroids or the moons of Jupiter. They'll also have applications right here at home, leading to more efficient electronics, better materials for construction, and more advanced robotics. The cold of deep space is a formidable challenge, but by learning to conquer it, we are paving the way for the next giant leap for humanity. Thanks for joining me on this deep dive into the chilling world of space mining technology. If you found this fascinating, make sure to hit that like button and subscribe for more explorations into the future of science and engineering. Let me know in the comments what other deep space topics you'd like to see covered. See you in the next one.